Okay, so let's talk about momentum conservation. So I posed the question, when is it useful? And if I didn't quite get a chance to write down the answer on the board, I said it, but I didn't have a chance to write it down. So here it is. When is momentum useful? It's useful when you have a multi-object system. So you have a bunch of different things involved, and they have some kind of unknown or potentially very complicated internal interactions. So things that are colliding within the system, maybe colliding multiple times. But here's the beauty of that. They are all internal. And if they're internal, we have Newton's third law to thank for the fact that quantity called momentum is conserved. Because we know, no matter how weird, how often, or how plentiful those internal interactions are, they're all dictated by Newton's third law, which means that when one thing hits another, the other one feels the force back, right? For every action, there's an equal opposite reaction. And what it turns out is that the consequence of Newton's third law is that when one thing loses momentum, another one gains momentum, those changes are equal and opposite. So we're forming now a new conservation. So those internal forces, which are of course Newton's third law, means that when one object loses momentum, the other one gains it, but the sum of those two, which is the system momentum, is conserved. So if you have a system where it's left alone by the outside world, if there's no net external force, then the system momentum is conserved. Any internal collisions that they're going to experience, just take momentum from one thing, give it to another, the total is the same. So what I want to do now is I want to show you an example with numbers. So I had before this idea of two things sliding across the surface, colliding with each other, and then bouncing off. And I purposely made this horizontal, frictionless, brickless, I guess. I don't feel like writing that. Okay. And let's throw in its no air resistance, right? We're doing everything we possibly can to let A and B be left alone, right? So nothing from outside is bothering them. The only thing of note that's going to happen to either one is going to be their collision with each other. So this system, this A and B system, is basically isolated from the outside world, and the only thing that's going to happen when they collide, potentially, is that one is going to give momentum to the other, but the total will remain the same. So let me give you some numbers here. Let me say that this is coming in at 3 meters per second, A is coming in at 3 meters per second, and B is coming in at 4 meters per second into the collision. And let me give you their masses as well. Mass of A is going to be 1 kilogram. Mass of B is going to be 2 kilograms. So let's go ahead and do a computation here. I'm going to tell you that A comes out of the collision at 5 meters per second. And I'm going to ask you, how does B come out? And we can answer that even having no idea what the collision force was like. How many newtons was it? How many seconds did it last? Doesn't matter. We can do it. We just want to make sure that all the momentum that's in the system to begin with is still all there at the end. So let's do that. Momentum of the system is conserved. Whatever momentum is in there to begin with is all there after the collision as well. So momentum of the system, of course, that's the momentum of A and the momentum of B collectively. There's going to be some trading between those two. That's what the collision force does, is it takes momentum from one and gives it to the other. but total has to be the same. Now momentum itself is m times v. And hopefully you don't mind if I don't write the whole thing out on the other side, just change the initials to finals. So this is like unfurling some big long scroll because we started from the beginning and this equation is just getting longer and longer, right? How many subscripts are we up to? We're up to 1, 2, 3, 4, 5, 6, 12, right? So 12 subscripts. We've got A's and B's and initials and finals abounding, okay? We could even go one more. This is a vector, right? So we learned that any vector equation can be taken apart into two equations of its components, right? The one that we most often did that with was Fnet equals MA, right? Fnet and A are vectors. We almost never used it as a whole. On homeworks 4 and 5, we used Fnet x equals MAX, Fnet y equals MAY. Remember that? It's easier to think of these complicated vectors as being decomposed onto x and y axes, right? So I guess I'll go ahead and write that out. At this point, let me just give up on trying to write it all in a row. I'll give you a little roadmap. So we'll first put in the A's. A, oh, and then, whoops, and then B's. A and B is my system, right? So here's my roadmap. A and B, that's my system. This is the initial side, right? So I'm going to put an initial subscript. I'm going to put it only on the velocities, by the way, right? The mass can't change during the collision. But the velocity can, right? So this is my initial side. And this will be my final side. I just switched those to finals. And then, of course, these are all x components. So x, x. This whole equation is an x equation. So let's see, how many subscripts is that? That's for 16? I think it's 16 subscripts. Plus another 16 more for the y equation. 32 subscripts. That's a lot, right? But necessary, because for a mass, I just need to say, is it mass A or B? But for the velocity, there's a lot that I need to nail down. Velocity of what? A or B? Is it before or after the collision? Is it the x or y component, right? So that's why there's this kind of cascading waterfall of subscripts coming off the velocities. So until you get really good at writing it straight, I wouldn't write it straight in a row. I would put kind of the MBs as empty shells and then fill in the subscripts kind of in sheets in order, okay? So let me show you how we would implement it in this problem. Now this problem is a one-dimensional collision, right? It's just a single axis, so I don't really need the y equation at all. I just need the x equation. So let me use this, and let me go ahead and start plugging into that. Okay. Now this is an x, these are x components, right? So I need to choose an x-axis. Let me choose, for lack of any reason otherwise, I'll pick x to be to the right. And then all these speeds that I was given need to be converted into components, right? Remember, we're back to vector land here. So you can't just put in the speed like you were working with energy. You have to put in direction. So what would this velocity direction be? Negative. It's going the same way as the positive axis, right? Yes? How about this one? Negative. How about this one? Negative. All right? So now we've made them velocity components. That's the beauty of one dimension, of course, right? no SOHCAHTOA grab. You just need to add plus and minus, right? So let's throw it in here. My mass is 1. My velocity of that mass is plus 3. My second mass is 2, and its velocity is minus 4. So there is the initial momentum of the system. What do I get at? 3 minus 8, that's minus 5, right? Minus 5, sorry, this is not a division symbol. I'm just trying to show that this collectively is minus 5. And the units of momentum, again, are minus 5 kilogram meters per second. That is how much system momentum has at the beginning. The collective system momentum is actually to the left. It came out to the left. Any ideas why it came out to be the left, even though I have both rightward and leftward moving pieces? Why did the left one, why did it ultimately come out to the left? This one's more mass and faster, so there's more leftward momentum in the system to start with than rightward momentum. So this is the overall system momentum. We have to make sure it's all there at the end. So let me ask you this. Is it possible for both of them to stop dead after this collision? No. Because what would be the momentum of the system if they both stopped? 0. And 0 is not negative 5, right? So no matter what happens, no matter how they strike each other, if they do just a little collision or a big collision, doesn't matter. All this momentum that's there at the beginning has to be there at the end. So let's figure it out. We clock our 1 kilogram mass going minus 5 at the end. Then our 2 kilogram mass has an unknown final x velocity. Now you guys can perhaps do that by inspection. What's the answer? 0. Minus 5 equals minus 5 plus, well, that better be 0, right? So what you notice is that mass B, or sorry, mass A rather, carries away all the momentum that the system had collectively, single-handedly afterwards, right? All the system momentum we see at the beginning is all carried by A, so B doesn't have anything to do. So solve here, or B actually stops. And my initial drawing of an arrow was a bit of a red herring. B doesn't actually go anywhere. It actually stops as a result of this collision. There are lots of possibilities, right? It really depends on the relative incoming velocities and incoming masses. It wasn't possible for them both to stop here in this case, but they could. If you calculate that you have a rightward momentum and a leftward momentum that are equal and opposite to begin with, then 0 is the sum. So if the system momentum had been 0 to begin with, they could have both stopped at the end and it wouldn't have been a violation of momentum conservation. However, here, because we calculated that the system had leftward momentum, there is no way that they could both stop. In fact, you have to have that there is continued leftward momentum. It just happens to all be carried by A at the end, so B can stop and take a break. Now notice how simple that was. We did not have to worry how much force did they exert on each other. We did not have to worry about the duration of that force. All we had to do was to recognize that it was internal. And if it's internal, the only thing that's going to do is going to trade momentum from one to the other. And all we did was make use of that idea and say, okay, well, if the momentum's got to all be there, we can figure out the final missing piece, right? How fast is B going? If we know the incoming velocities of the two, we know the outgoing velocity of one, we can infer the outgoing velocity of the other. Are there any questions on that example? Okay, so this is, again, a very incredibly powerful idea. You could have, let's say, a bunch of particles flying around, having all sorts of various collisions at various times, right? You could have a large number of these collisions. You could have, you have no idea how much force is generated in those collisions or how long they last. But if you can identify this and say, there is no net external force from the outside world, it's what I'll call an isolated system. No matter how many times they feel like colliding with each other, when you count up the momentum of the entire system, it's always going to be the same. So if you start watching the system, they all have some individual momenta, you add those up very carefully. Then you let them collide 1,000,000 times, and nobody individually has the same momentum at the end because everybody's gotten hit by somebody. And yet, the total momentum is still exactly the same as long as the system is isolated from the outside world, right? So that's a pretty powerful tool. Now, how are you going to implement this in lab? Well, as you can probably guess, I don't have a frictionless surface for you. There's no way you can truly get rid of friction. There's no way you can truly get rid of air resistance. You can't really get the net external force to be 0. What you can do is you can make it look bad. You can make it look 0. How is that? The net external force just has to be much less than the internal collision force. Then we have hope that this is sort of 0-ish, right? So in reality, you can use this, so if you call this the kind of the clean, perfect momentum conservation, when a true system is truly isolated, of course this never happens. But the game of physics is to say, well, that's not technically true, but it's very close to being true, close enough for our purposes, right? So what I want you to do in your lab next week is you want to make these external forces look bad. There's going to be some friction, there's going to be some air resistance. How do you make it look bad? Collide the carts very violently. So this is one of those times where, you know, don't go extreme, but being timid is not a good thing. You want to collide them pretty hard. And the harder you collide them, don't have them flying off the track or something, but the harder you collide them, the better your results. And the reason why is you want the internal interaction to be the major show, right? In fact, that's kind of the definition of a collision, isn't it? A collision, what is it? It's a violent event. Violent respect to what? Violent respect to whatever else was going on, right? So you will get better results if you can make the internal collision force the big event. Because the internal collision force will just trade momentum amongst the two things, and you should see it all there at the end. Only external forces can change the momentum, but you want them to basically look bad, right? You want a violent collision force that drastically changes the momentum of each thing individually, but conserves the sum of the two. If there's some annoying external force like air resistance that's going to chew off a little momentum from outside, that's okay. You're not going to get perfect results, but you want to make the internal collision the big event. And in fact, I've heard it said, when is momentum conserved for collisions? Always. Because what is a collision? A collision is a violent event where the big event is inside the system and not outside. Okay? So that is a one-dimensional example. The next thing I'm going to do is just show you a two-dimensional example. So a two-dimensional collision. Are there any questions before I do that? Okay, so let's do just a calculation that's very similar in spirit, but may have more than one axis going on. So this is an example of a 2D collision. You're going to have some of these on your homework, and if you don't like these problems, you are not going to like them because of the math. Okay? It has nothing to do with physics. The concepts are straightforward, physics is often the thing you do to get from your brain to your paper, right? So looking at the situation and being able to decide what technique to apply, what equation to use. And then from there, anything you're doing is really just math, right? It's about solving for something, okay? So a lot of times I hear from students, I get what's going on in the class, I just don't know what equation to pick. Well, that's physics, right? So actually finishing up the calculation, that's math. Physics is often what you do at the beginning to select out of your arsenal something appropriate, right? What technique do you apply? And that involves understanding the concepts that underlie all this stuff. So let's go ahead and do a collision. This is going to be a top view. And it's going to be a horizontal, very smooth surface. An example of this, if you've ever played a game called air hockey. Does anyone, you guys know air hockey? Okay. So it's this flat surface, and there's little holes in the table that air blows out, and it gives you about as cushion of a friction-free surface as you're really going to see in the outside world, right? So I'm going to draw a puck sliding across this table, and it's going to hit another puck, B. I guess let me give you some figures. Just let's make this quantitative. I'll say that A comes in at 5 meters per second, and let me give you the masses. Mass of A is 1 kilogram, and B is 2. So this is the initial situation. Now, it's not my drawing is bad. I didn't mean to have A coming in. I don't want A to have a head-on collision. Because if A has a head-on collision with B, it's just a one-dimensional example like the one I did. I want it to be a glancing collision. So I want to have A kind of hit off-center. So what happens afterwards is it looks like this. A goes flying off like this, and B goes flying off like this. This is my final situation. You may have seen something like this on an air hockey table. Another place you might see this is when you're playing pool, right? So you have some kind of glancing collision that allows you to suddenly have motion in a second dimension. So now, even though we weren't moving in the direction that's up and down on the board, now we are. And here's what I'm going to give you. I'm going to give you that A goes off at, B goes off at 2 meters per second at 45 degrees. And I'm going to ask you, how much speed and at what angle does A go off with? So momentum conservation will help us figure out both of those things. Now you may be surprised that there are 2 unknowns, but having 2 unknowns simply means we need to have 2 equations to find them. So we are going to have 2 equations. There's going to be an x equation and a y equation. This follows the same kind of mathematical scaffolding as we were doing in homework 4 and 5, right? Classic 2 equations, 2 unknowns. One from the x, one from the y. Okay? So I'm not going to do all the algebra at you. I'm just going to kind of sketch out what you would do, and I'll give you the results. Try it at home. Make sure you can get it. I'm going to go ahead and pick my axes like that. And I'm going to resolve everything that's going on into x and y. So I don't want to deal with diagonal things. If it's diagonal, it's going to get split up into pieces. Luckily, for A, initially it's all x. So that's simple. But all the complication, of course, comes in at the end, right? At the end, both masses have components in both directions. So this is where you pull out your component skills again. Let's make sure you can at least give me the signs of the components. What is the sign of this component? Plus or minus? Plus. Plus. How about this one? Plus. How about this one? Plus. How about this one? Minus. Okay? And then, of course, SOHCAHTOA comes next, right? In this case, just to give it away a little bit, both x components are going to get cosine, both y components are going to get sine, right? So then you're just going to do your momentum conservation in the x and y directions. So the momentum of the system is conserved, and you're going to apply that for x and y. And again, why can I say that? Because the net external force on this system is 0. So I purposely did this on a horizontal frictionless air hockey table so that these guys could be left alone from the outside world. The only thing that they have to do is to bump into each other, and that trades momentum. It doesn't increase or decrease the momentum of the system overall. So let me sketch out the x direction first. What's going on in the x direction? A is moving in the x direction to start with. B is doing nothing. And then afterwards, this is the initial. And then afterwards, they both go off together. They both have x velocity afterwards. So I'm just including the components, right? So that's very similar to the examples that I just did, your x component. In fact, you can probably tell me the system momentum in the x direction. Is it positive, negative, or 0? Positive, right? It's positive beforehand, so it's got to be positive afterwards. Why is it positive? Well, beforehand, there's B is stopped, but A is going to the right. Positive. So afterwards, they have to have that, all that x momentum has to be there. So the same sum of the momentums here is going to, or momenta here is going to be the same here. Let me ask you this. This came in at 5 meters per second. Is A going to be going slower or faster afterward? Slower. Why? Had to give some momentum to B, right? So A is going to slow down. So A slows and B speeds up, but the total momentum has to all be there. Okay? How would you set that up? Just briefly, I don't want to write it all out because it's going to just be very laborious. Mass of A times plus 5 meters per second plus 0 because B is not doing anything, right? Then mass of A times this component plus the mass of B times this component, right? That equation is going to have both unknowns in it, right? It's going to have both VAF and theta in it. In fact, they're going to appear in this component. So no worries. That equation is going to have 2 unknowns, but you're going to have a second equation, so don't panic, okay? Let's talk through the y direction. Are there any questions on the x direction before I do the y direction? Yeah?
Explain again why when A slows up, why B speeds up.
Why B speeds up?
Yeah, why mass A slows down and why.
Well, initially, mass A is carrying the entire x momentum of the whole system because B is stopped. So if some momentum is going to go into B, it has to come from A, right? So if B is going to speed up, A has to slow down. Otherwise, you'd have more momentum afterwards in the x direction than you had at the beginning. Okay, so let's talk in the y direction. What's going on in the y direction to begin with? Nothing at all, okay? A and B, as far as the y direction is concerned, nothing is happening. So what is the y momentum? 0. The system momentum in the y direction is 0. So what does it have to be afterwards? 0, still 0, right? How is that possible if A is moving upward and B is moving downward like this? How is that possible? Can that still add to 0? Sure it can, right? These are vectors. So a positive momentum and a negative momentum can still add to 0. No problem. In fact, this helps us to figure out that the system, the y momentums, I guess I'll call it PAY and PBY, are always equal and opposite. If they have to add up to 0 all the time, then whatever value one has, the other one has the opposite. So there's your setup. You have two equations, two unknowns, and it's ugly and horrible and whatever. It's two equations and two unknowns. They're usually ugly. And these coefficients are not going to be like they're in math class, 2, 3, 7, all these integers. Okay, they're going to be ugly decimal values. Okay, but it's math. Okay, so you just solve, and let me tell you what the answers are. You can try this yourself at home, and let me know if you have any difficulties getting these. This is 3.52 meters per second. And this is about 52.2 degrees. So don't stress out too much if you don't get exactly those rounded off values, but those are approximately correct. And by the way, even though two equations, two unknowns is annoying to solve, you shouldn't need all 5 guesses on WebAssign to get them. The beauty of two equations, two unknowns is you can always check them, put them back in the equations, and make sure that they work, right? So you have built-in error checking right there. You're trying to solve for the solution to these two equations. When they come out, you can say, are these two the solution to these two equations? Now, what if you're sure you did it right? You keep on plugging them into the equations, and they keep on agreeing, but it's not correct. Well, that means, of course, that the equations themselves were set up incorrectly. So make sure the equations are right before you start solving them, right? So make sure you have all your pluses and minuses accounted for, things like that. Are there any questions on this? Okay, so the math might get a little bit more challenging, but the ideas are the same. We have a system which is relatively isolated from the outside world. Internal collision force is straight momentum. You're just trying to make sure that the momentum is all there somewhere afterwards, just like it was at the beginning. So our positive x momentum that we had at the beginning has to all be there at the end. Our 0 y momentum that was there at the beginning has to all be there at the end. And that's possible because, again, the y momentums that they picked up are equal and opposite. Okay. Any questions before I move forward? All right. So these are what we've been doing lately are two of the most powerful ideas in all of physics: energy conservation and momentum conservation. And so what I want to do next is I want to talk about them together. So when can you use momentum conservation? When can you use energy conservation? When you can use them both? When can you use neither? Okay? If you understand that, that is a extremely important, you understand a lot about physics. So what I want to do next is I want to start comparing these two. These are independent things, so we should take a look at when it would be appropriate to use one versus the other. So let's take a look at momentum conservation and I'll talk about mechanical energy conservation. So remember when we say E, we really mean not all energy. Of course, you're talking about every energy form, and it's never destroyable or creatable. When we say E, I mean a certain subset of energies, which we call kinetic and potential. So that is conserved when there's no non-conservative work, right? So our master energy equation looks like this. Where E stands for something called mechanical energy, which is kinetic plus potential. And we can count on it all being there at the end if we don't have some of these annoying other types of things, which are really just a catch-all for other forms of energy that are more complicated and we don't want to deal with them. Examples being friction, which can take energy completely, mechanical energy completely out of a system, turn it into thermal. Or we talked about an applied force, where you can just pump energy in, right? I can lift an eraser to the top of the board and put a mechanical energy into a system. So if we are expecting mechanical energy to be conserved, we have to make sure that there are no annoying forces like friction in the situation. Momentum conservation, it's a different story. I can use that when the net external force on a system is 0. It's about the system being isolated from other places. Those are two different things. Now they both involve forces, don't get me wrong, but in momentum conservation, the big concern is where's the force coming from, okay? Is it coming from outside or is it inside? I like to call the, so I'm asking the question, internal versus external. I'll make a little Venn diagram here. So I'm cataloging my forces. And one way to categorize forces is if they're internal to a system or external. And those two things in my Venn diagram don't overlap, right? Because it's not possible to be simultaneously both, right? So I like to call the momentum conservation, it's like the Las Vegas conservation, okay? Momentum is like Las Vegas. You heard the saying, what happens in Vegas stays in Vegas? Yes? Okay? So as long as it happens inside the system, momentum conservation doesn't care. Okay? If it's coming in from outside, that's a different story. But as long as it's happening within the system, momentum is happy. Momentum is conserved. No matter what happens in the system, as long as it's in the system, momentum is conserved. Okay? Now that's a very different thing that energy is asking about. Energy is asking about conservative or non-conservative. Conservative forces or non-conservative forces. And those, of course, again, don't overlap because you can't be one and the other. Conservative forces, one example is gravity. That's the big one we've looked at so far. We'll see others later in the course, and other examples in the force from a spring. So gravity is one. And remember, the reason why it's conservative is because whatever it takes away from you, it'll give you right back, right? So gravity will take energy from kinetic as you fly up into the air, and then it'll say, here you go, you can have it back as you fall down. A spring is kind of the same way, by the way. We'll get into springs a little bit later, but you know a spring works like that too, right? If you compress a spring, it doesn't just stay there, it'll fly back at you, right? Example of non-conservative forces, friction is the big one, and applied force is another. These are things that can either take energy, mechanical energy out of a system or put it in, right? So basically this is the big wide world of forces, and we have various ways of categorizing these forces. Internal or external, conservative or non-conservative. So we do have some regions of overlap here. So one force, it could be internal and conservative. It could be external and non-conservative, right? These are various combinations, right? So these four regions of overlap are actually our interest. So let's take a look at this, for instance, right here. Okay, so we have a system where there's only internal forces. So if there's only internal forces, can we use momentum conservation? Yeah, we can. And those forces that are internal are conservative, so can we use energy conservation? Yes. So there, we're great. We can use both conservations. Let's go over here. So we have a system where there's only forces internally. Can we use momentum? Yes. But those forces of collision inside, they might be like this. What happens to the energy there in those collisions? It goes to heat. So we can't use energy conservation. So one of the quantities is conserved, the other one is not. Okay? Let's go over here. We have external forces now, so that's going to ruin momentum conservation, right? Can't use momentum anymore. Momentum, can't use it. So it's the force coming in from outside. But the force that's coming in from outside, maybe it's gravity, it's a conservative force. Can we use energy? Yes, we can. That's where we use energy, and the new technique, momentum, is not really very useful. Okay, what if the force is coming in from outside and it's something like friction? Can we use energy? Mechanical energy is not conserved. There it seems like we're stuck. So I'll talk about what we would do in that case. So the whole idea is that the forces are the cornerstone of how the outside world interacts, right, with an object. Forces are the pokes and prods acting on an object from the outside world. When we were doing Newton's second law, F net equals ma, we didn't make any distinctions of this type of force or that type of force. They're all just forces to throw in there, right? So we throw them in, normal force, gravity, friction, we just throw them all in, right? Homeworks 4 and 5 are all about that kind of thing, right? Now, when we have the great wide world of various forces, then we can go ahead and we can say, let's start putting them into categories, right? What kind of category is this force or that force? And we found that the most important category for energy was conservative forces and non-conservative forces. If it's something called a conservative force, it can take energy away from kinetic, put it into something we call potential energy, and you can easily get it back. And we liked those forces. Other forces like friction didn't play nice, so it didn't work. Then we got to momentum conservation, and the big question was, is it a force that comes from outside? Because all the forces that are inside, we can ignore them. Right? As long as it's inside, all it does is trade momentum amongst members. It doesn't matter what kind of force it is in terms of conservative or non-conservative. What matters is if it's inside or outside. As long as it's inside, we can use momentum conservation. This right here, if you understand this, this is a massive understanding in this course, okay? It's basically, you understand a lot about this course, you understand a lot about physics in general, if you understand when these conservations can be applied. What I'm about to do, and obviously won't have very much time for this today, what I'm going to do is go through a whole series of scenarios. Like, this is the system. things that you might see on the exam. I'll just give you some kind of situation. And I'm going to just talk through which of the conservations I can use. Okay? So what I'm about to do is a scenario. I'm going to present that scenario. I'm going to ask, is momentum conserved? I'm going to ask, is mechanical energy conserved? And I should probably leave room for some comments. So, let's go ahead and see what we can do here in the next couple of minutes, and then we'll knock off for the day. So, first let me present the scenario very much like what we've been doing today. Two objects colliding. They do this on a low friction surface, and I'm going to treat my system together. So we decided, is momentum conserved in systems like this? What's that?
Yes.
Yes, for sure. So the net external force is 0. To the extent that we can neglect air resistance and friction and all these little annoying things that might change the momentum from outside. The collision that they're going to experience just trades momentum. Okay, now, if momentum is the Las Vegas conservation, as long as it happens in the system, no big deal, it stays in the system. But then mechanical energy is like your mom, she's a little more nosy, right? It's like, I know it happened in the system, but why don't you tell me what that force was like, okay? You can tell me what happened, okay? So what kind of collision is it that happened in there? Did it expel energy thermally or not? Well, it could be either. We don't know. I mean, there's lots of different ways things can collide. So the answer could be yes, maybe, or it could be no. There's both possibilities. Because now we're being nosy, and even though it's internal and momentum conservation is perfectly happy, on the flip side, we have to be a little bit more nosy about what that internal collision force was like if we want to know about energy. We basically want to know if we're on this category or this category, right? Was it an internal conservative, internal non-conservative? One option is that maybe the collision happened by a spring. So maybe you took some of the kinetic energy of the system, you put it into the spring was compressed during the collision, but then of course a spring compresses, says, I'll store this for you, but here, take it back. So it comes back, right? And so we are expecting to see the initial and final kinetic energy are the same because while it might have gotten momentarily absorbed into the spring during the active collision, the spring just stores it up for you and then says, here, take it back. So in these kind of systems, the kinetic energy of the system is the same before and after. We have a name for these kind of collisions. We call them elastic. Okay? They are elastic because either you literally have a spring that's between the objects as they're colliding, or the objects are just springy, right? They're like rubber balls or something, right? When you think of a rubber ball, when it collides, it compresses, but it doesn't stay compressed, right? It says, take that energy back, please. Or the other option is that the kinetic energy gets turned into thermal energy during the collision, and then you ain't getting it back, okay? So, like this, when you collide like that. So then, you might say, well, isn't the energy all still there? Yeah, but part of it is thermal, right? The temperature of the blocks is increased. So it's not mechanical anymore, right? So then, the kinetic energy of the system will actually decrease. And we have a name for this. It's called inelastic. Okay? So we'll take a look at both possibilities on Monday, and we'll then do those two collisions in your lab next week. Okay, that's it for today.